Hi, welcome to my video number 6 about the best methods to alkylate carbon nucleophiles. This presentation is about the alkylation of enamines. These are almost never target compounds but just synthetic equivalents of aldehyde or ketone enolates and are usually hydrolyzed when no longer needed. Thus, this chemistry is inherently wasteful because a secondary amine is needed. However, the formation and alkylation of enamines does not require strong bases or low reaction temperatures, what is a great advantage. Enamines, like enolates, can be alkylated at carbon or at the heteroatom, depending on the polarizability of the electrophile, the solvent, and on the precise structure of the enamine. Bulky amines are usually quaternized more slowly than sterically more accessible amines. The initial product of the carbon alkylation of an enamine is an iminium salt. In the presence of bases, such as tertiary amines or unreacted enamine, this iminium salt can be converted into a new enamine by deprotonation and be alkylated again. Thus, going the enamine route is no safe strategy to prevent multiple alkylations. There are some alternatives to the stoichiometric formation and alkylation of enamines. In recent years, for instance, the chemistry of enamines formed in catalytic quantities only has been intensely investigated, but numerous side reactions can occur. These include aldol additions, direct alkylation of the amine at nitrogen, and Mannich reactions, that is, the alkylation of aldehydes or ketones by iminium salts. Further alternatives include boron, titanium, or alkali enolates, the latter being the most basic and nucleophilic. Silyl enol ethers can also be alkylated at carbon, but this usually requires acidic reaction conditions and strong carbocation-like electrophiles. A number of different methods exist to prepare enamines. The most common strategy is the condensation of secondary amines with aldehydes or ketones, and many examples have been reported. Care must be taken to prevent aldol additions from occurring, in particular for enolizable aldehydes. A second, much less common strategy is the isomerization of allylamines. These can be prepared either by alkylation or reductive alkylation. This strategy can be particularly useful for the preparation of aldehyde-derived enamines, because no aldehydes will be present in the reaction mixture during enamine formation. Aldehyde-derived enamines can also be conveniently prepared from epoxides and in excess of a lithium amide base. This reaction proceeds by initial lithiation of the oxyrane, followed by nucleophilic ring opening of the epoxide and beta elimination of lithium oxide. Also, terminal alkynes, which may be viewed as dehydrated aldehydes, can serve as starting material for enamines. In the given reference, 2% of a tungsten catalyst was used to bring about the addition of the amine to the alkyne. Finally, one-pot procedures exist for the partial reduction and dehydration of amides, which can also be used to prepare formerly aldehyde-derived enamines. The main advantages of the enamine strategy for alkylating aldehydes or ketones is that the starting materials are readily available and that neither the preparation of enamines nor their alkylation requires anhydrous solvents, low temperatures, or strong bases. The main disadvantages are that enamines are weak nucleophiles that only react with strong alkylating reagents. And then there is the requirement of stoichiometric amounts of a secondary amine, which ultimately is lost. Here are two examples from recent patents. In both, a pyrrolidine-derived enamine was alkylated with phenacylbromide and with ethyl iodide. After hydrolysis, only the first alkylated ketone was obtained in acceptable yield. The low yield of the alkylation with ethyl iodide may have been caused by competing N-alkylation of the enamine. Pyrrolidines are readily quaternized, in particular by methyl iodide, and here a sterically more demanding amine may have given a higher yield of ethylated tetralone. Sterically demanding enamines do not, however, necessarily undergo high-yielding alkylations. In order for an enamine to be nucleophilic at the beta carbon of the alkene, the lone pair at the tertiary amine must be able to overlap and push electrons into the empty antibonding pi star orbital of the olefin. If the amine is too bulky and the required conformer too little populated because of repulsion between the amine substituents and the vinylic beta hydrogen atom, then the enamine will not be sufficiently nucleophilic at a carbon. This was probably the reason for the low yield of this methylation reaction. A similar but slightly less crowded enamine already reacted at 15 degrees Celsius with methyl iodide and gave, after hydrolysis, a high yield of alpha-methylated aldehyde. This same enamine even reacted with isopropyl iodide, despite the high tendency of secondary alkyl halides to undergo elimination. Some enamines form part of so-called push-pull olefins, that is, alkenes with one electron withdrawing and one electron donating group, as in the starting material of this example. Such enamines are much less basic and nucleophilic than, for instance, those of the previous examples. Nevertheless, with a huge excess of methyl iodide, it was possible to methylate this deactivated enamine. Strangely, a strong base was required to regenerate the push-pull olefin in this specific case, but usually weaker bases should suffice for this deprotonation. Enamines can also be alkylated with electron-deficient alkenes, such as acrylates or acrylonitrile, as in this example. Direct alkylation of ketones or aldehydes with such Michael acceptors often yields mixtures of polyalkylated or aldol addition products, and the enamine strategy is often superior to the direct alkylation. In this example, an acetophenone-derived enamine was alkylated enantioselectively with a benzylic propagyllic acetate and a chiral copper diphosphine complex. Copper reacts quickly with terminal alkynes and strongly stabilizes propagyllic cations. In this way, propagyllic substitution can often be catalyzed effectively by copper salts, as was the case here. Let's have a look at potential side reactions. Because the initially formed iminium salts can be deprotonated by unreacted enamine to yield new enamines, multiple alkylations of enamines are possible. In both these examples, the twofold alkylation was intentional, but these may also occur to a lesser extent without an excess of alkylating reagent or base. A further potential side reaction is the cyclization of products resulting from the alkylation of enamines with electron-deficient alkenes. This is, however, only a potential issue for a relatively small group of products. The exact selectivity of polyelectrophiles is not always easy to predict correctly. A frequently used electrophile is benzyl chloro or bromoacetate. Surprisingly, some nucleophiles are benzylated by this reagent, as was the case in this example. Besides the already mentioned quaternization of the amine, enamines are readily oxidized by air or other oxidants. Furthermore, the intermediate iminium salts can also alkylate the enamine, ketones or aldehydes present in the reaction mixture. That is, Mannich-type reactions can occur. Under suitable conditions, enamines can also undergo 2+2 cycloadditions with electron-deficient olefins or alkynes. Photochemistry is experiencing a revival, and reactive intermediates, including enamines, can give the weirdest reactions when irradiated with intense light, including, for instance, beta-alkylation. Here are some more examples of enamine alkylations. Despite its limitations, it's a reaction worth keeping in mind because on occasions it can be a practical way for the large-scale preparation of certain ketones or aldehydes. My next video will be about the alkylation of 1,3-dicarbonyl compounds, which are readily available and versatile synthetic intermediates. See you there.